Hello. So today's video is on Fourier and Laplace transform. So this topic is a bit long. It consists of 11 questions. So first question is from 2019 June, which reads as: consider an array of atoms in one dimension with an ensemble average periodic density distribution as shown in the figure. So this figure is given where these bars are placed at A, 2A, 3A and 4A. If K is a wave number and S of K delta denotes the Fourier transform of the density correlation function, the ratio S of K delta upon S of K0 is. So the first thing first is that density distribution, by seeing the graph, what do you see is we see a rectangular function, right? So we write the density distribution function can be written as density distribution function can be written as rho of x equals to 1 over delta rectangular x minus a plus rectangular function x minus 2a plus rectangular function of x minus 3a. Similarly for the fourth one, that is x minus 4a. Okay, now where this rectangular function is defined to be where rectangular x minus na is equals to 1 for x minus na is less than delta by 2 and 0 for x minus na less than greater than delta by 2. Now the Fourier transform of this function of rectangular function is is a sinc function. It can be solved by doing the integrals. I will write it just simply. F of t, if f of t is a rectangular function of t by tau, then the Fourier transform x omega is equals to minus infinity to infinity rectangular function. We will write this, and then it can be solved for the limits, and then it will come out to be tau sine omega tau by 2 divided by omega tau by 2. Here tau, the t by tau is missing, so therefore it won't be there in our calculation. So I will write the Fourier transform of rho x as Fourier transform of rho x is f of k delta is equals to it will be a sinc function which is written as this. It is tau sinc of omega tau by 2. Okay, now f of k delta is sine of k delta by 2 in the limit minus delta. This Fourier transform is done in the limit delta by 2 to delta by 2 minus delta by 2 to delta by 2. So we will get the following, which is this one, k delta by 2, which can appropriately be written like this: 2 by delta sine k delta by 2 divided by k. Okay, now we define the density correlation function in Fourier domain is written as the density correlation function in Fourier domain is written as S of k delta equals to f of k delta f asterisk k delta. Okay, now what we get is 2 by k delta 2 by k delta sine of k delta by 2. This becomes the square, since sine of the complex conjugate of sine is the sine. So now another thing is, now another part which we have to take the ratio of is s of k0. So when the limit is when the limit is delta tending to 0, this function sinc function becomes 1. Okay, so what we do here is it becomes 1. Therefore s of k delta by s of k0 is 4 by k square delta square sine square k delta by 2. Okay, so by this solution, option 4 is the correct answer. Option 4 is the correct answer. Okay, now another question is from 2019 December, which reads as: the function ft is a periodic function of a period 2 pi in the range minus pi to pi. It equals e to the power minus t if ft is equals to minus infinity to infinity. Cn e to the power int denotes its Fourier series expansion. The sum Cn square is. In order to determine the coefficient modulus of coefficient square, what we do is we will use Parseval's formula. Using Parseval's formula, summation minus infinity to infinity, it is defined like this: Cn square equals to 1 upon t minus infinity to infinity f of t square dt. Now here t is a time period which is 2 pi. Okay, so 1 upon 2 pi minus infinity to infinity, and f of t is given to be e to the power minus t. This is okay, so this becomes minus t square dt. Now this comes out to be 1 over 2 pi. Oh sorry, the limits are not this one, so it will be minus pi to pi. Limits are in the range minus pi to pi, so 1 over 2 pi minus pi to pi e to the power minus 2t dt. Then this solves, then it can be solved like this. It will come out to be minus pi to pi. This becomes minus 1 upon 4 pi e to the power minus 2 pi minus e to the power 2 pi 1 over 4 pi e to the power 2 pi minus e to the power minus 2 pi, and then this becomes 1 over 2 pi. We will do the little calculation manipulation. This becomes 1 over 2 pi sine hyperbolic 2 pi. So from this, option D is the correct answer. I don't have the options right now, but this is the actual answer. Okay, you can check in the paper. This is the correct answer. Now another question is from 2018 June. The Fourier transform minus infinity to infinity dx fx e to the power minus kx of the function fx equals to e to the power minus x is. So we can do it either by the short trick or we can go for the longer way. First I will go with the longer way. This is done as f of k is a Fourier transform of fx. Okay, so this comes out to be minus infinity to infinity f of x e to the power I k x dx. Okay, now here f of x is given to be this e to the power minus modulus of x. This becomes minus infinity to infinity, limits are same, e to the power minus x e to the power I k x dx. Now another one, we will break the integral into two, minus infinity to 0 e to the power x e to the power I k x dx. Why we are doing this? Because x is in the modulus, that's why we are doing the division of the integral 0 to infinity e to the power minus x e to the power I k x dx. After doing the integral, we get 1 plus I k of x, 1 plus I k, minus infinity to 0 plus e to the power minus 1 minus I k x minus 1 minus I k, 0 to infinity. Okay, now this comes out to be 1 over 1 plus I k minus 0 plus 0 plus 1 minus I k. This becomes 2 plus 1 plus k square. Okay, so this is the answer, and if you will check, this is the option 3. Now for the short trick or just a formula. This is not a short trick actually, it is just a formula. Fourier transform of e to the power minus a modulus of x is equals to 2a over a square plus b square, and for our question a is equals to 1, so we just have to put in this and we will get this particular answer. Okay, now another question is from 2017 December. It is on the Laplace transform. Okay, this question is based on the Laplace transform. Okay, so here the Laplace transform, I will read the question. Consider the differential equation dy by dt plus ay is equals to e to the power minus bt with the initial condition y of 0 is equals to 0. Then the Laplace transform y of s of the solution y of t is. So we will take the Laplace transform of the differential equation. Okay, now we will do the Laplace transform. L of dy by dt plus a of ly is equals to L of e to the power minus bt. Okay, now it is already known to us that Laplace transform of any derivative with respect to here it is given as s of y of s. It is a Laplace transform of y of t and minus function at which t is equals to 0, in which t is equals to 0. So here when we will put this into the above equation, this becomes s of ys minus f of t equals to 0 plus a L of Laplace transform of y is Laplace transform of y, small y, is ys. Therefore this small capital ys. So this becomes this, and what else has to be done? Laplace transform of e to the power minus bt is given as, it is 1 over s plus b. It is the Laplace this is the formula which one should remember, that Laplace transform of e to the power minus bt is 1 over s plus b. Okay, now this becomes s of y of s equals to 0, and now function at t equals to 0 means y at 0, this is y of 0 is equals to 0. This is already given to be 0, this is already given to be 0. Okay, this is already given to be 0. So this becomes y of that is 0 plus a y of s equals to 1 over s plus b. Now take y of s to be common, this becomes s plus a or equals to 1 over s plus b. Now Laplace transform of y of t is, that is L of y of t is equals to this. This comes out to be 1 over s plus a s plus b. This is the right answer. So only option 1 matches with the solution. So option 1 is the correct answer. Okay. So our next question is from the 2016 December. The Fourier transform of minus infinity to infinity dx fx e to the power minus I e to the power I kx of the function fx equals to 1 over x square plus 2s. So what we will do in this question is, in order to solve this integral, we can use complex integration technique, which we will replace x with z first of all by using complex integration technique. Okay, so this comes out to be f of z is equals to e to the power I kz upon z square plus 2. Okay, now for positive k we will choose a contour to be semicircle counterclockwise, that is counterclockwise in the upper half. So for positive k, contour is taken to be, that is semicircle, contour will be semicircle in counterclockwise direction, that is anti-clockwise in upper half. Okay, so this is the diagram. Root 2i, and the other point will be at the z is equals to plus minus root 2i. Okay, so this will become, this another point is at minus root 2i. So the upper half plane, that is for positive k, upper half plane is being considered. So singular points are, these are the singular points, by the way, singular points are z is equals to plus root 2i minus root 2i. Now what we do is minus infinity to infinity e to the power I kz over z square plus 2 dz. This can be solved as like this: 2 pi I residue of f at z equals to root 2i. At z equals to root 2i, this becomes this function becomes obsolete, that is indefinite. It becomes infinite, to be precise, to be infinite. So for such cases, when z is equals to root 2i, the denominator becomes 0. For such cases, denominator is being differentiated. So the concept to be learned is, if f of z is equals to phi of z over psi of z, where psi of a is equals to 0, that is the denominator is 0, but phi of a is not equals to 0, then residue is found out like this: residue of f of z is equals to a is phi of a over psi prime a. Okay, now we will do the following, that is, I will not write the same integral over and over again. I am just considering them to be f of z. Okay, so this becomes 2 pi I residue of we will take, it will be done like this, exponential of e to the power I k z over, when we will differentiate z square by 2, that will become 2z. So I will put that here, 2z, 2 will cancel, 2 will cancel, and this this integral this part is at z is equals to, by using this formula, we are using this formula here, so z is equals to root 2i, we will put z equals to root 2i, so pi I e to the power I root 2i k pi root 2i, I will cancel, this becomes pi by root 2 e to the power minus root 2 k. Okay, now this is for our positive k. Now similar set of procedure will be followed for negative k. This will become, we will choose the contour to be semicircle, and now in the clockwise direction and in the lower half, so same diagram but in the reverse direction. Okay, hold a sec. I hope this is fine. This is the middle. This is minus root 2i, and upper one is plus root 2i, which we already did it. Now we are doing for this case. This is minus r, and now it is clockwise direction. Okay, now same procedure, same thing, minus infinity to infinity e to the power I k z over z square plus 2 dz is equals to 2 pi I residue of f of z equals to f of z equals to minus root 2i. So this comes out, same procedure, same thing will be done, pi by root 2 e to the power minus root 2, not minus, it will be plus root 2 k. Only difference will be, here we will put here we will in this step we will put minus root 2i k, minus root 2i. Okay, when minus root 2i is put, then the equation, this step will become root 2k, that will be positive, exponential will be positive. So gk is equals to pi by root 2, that is the finalized form, final integral solution is minus root 2 k. Okay, so option D is the correct answer for this solution. Option D is the correct answer. Okay, so we did 2016 December. Now another question from the same paper is the Laplace transform. So what we can do is the Laplace transform of ft equals to t by capital T, which is in the limit of 0 less than small t less than capital T, and 1 when small t is greater than capital T is. So for this Laplace transform of there will be whole bunch of formulas will be used. So one should remember all the Laplace transform formulas. I will list them once if you want it. E to the power minus st ft dt. Laplace transform is defined like this. Remember this. Memorize it. E to the power minus st ft dt. Okay. Now here in our case it is it can be broken into two integrals, that is from 0 to t and another from t to infinity. Okay, so this becomes 0 to t e to the power minus st t by capital T dt plus t to infinity 1 e to the power minus st dt. Now this 1 over t can be taken out, not 1 over t, yes, 1 over t is taken out for the first integral. This becomes t e to the power minus st by minus s. Okay, now another one from the same thing. This will become 0 to t e to the power minus st, integrating by parts. Okay, so this will become, this whole will be of the forms, okay, not the we don't need to put the limits right now. Okay, now another one for the second integral, it will be e to the power minus st over minus s t to infinity. Okay, now another step is to solve the first integral only. 1 over t minus t e to the power minus st by s plus, not plus, this will become, again we are doing the integral of e to the power minus st. This will become e to the power minus st by s square. Now the limits are 0 to t. This is a bit clumsy. 16 to infinity, this is t also, 0 to t. Okay, now another one is e to the power minus st by minus s t to infinity. Now we will solve the whole integral, which comes out to be 1 over t minus t. We will put the limits, st by s minus e to the power minus st by s square plus 0 plus 1 over s square plus e to the power minus s of t by s. This comes out to be 1 over s square t 1 minus e to the power minus s of t. So only option that matches this answer is 1 minus e to the option B, option 2. So option 2 is the correct answer. Okay, so rest of the questions I will do in the another video of the same context. Okay, see you then.